start. Okay, so obviously in today's lesson we'll be looking at physical sciences. So hopefully, if we can be quick enough, we can manage to go through both of those questions. And again, I know there are 3 types. So those are just 2 types where we'll be looking at different types of forces. But before we even start with those question papers, I just want us to firstly remember the type of forces that we have. Let's just name them in terms of number one. Saying number one, remember, we've got forces in physical science. This is just a revision, LB. LB, are you still there?
Right, can you please repeat that? What?
So I was saying this is just a quick revision before we start solving those problems.
Yeah, okay, noted.
Yeah, so just make sure that in case if you want to ask me something, then you can just unmute, pose a question, then I'll just quickly stop from what I'm doing. And again, in case if the network is bad, just let me know, because I'm trying to do something of which let's discuss this towards the end of our lesson. Just make sure that we discuss, let's say, option number B. So just make sure, LB, that towards the end of the lesson, we just discuss. Maybe I'll remember exactly what I wanted us to. So in physical sciences, obviously, we've got forces. So we've got different types of forces. Let's firstly talk about the first type of a force. Remember, the moment we talk about a force, then we talk about something which has got a unit of Newton. So let's see. The first type, we can talk about gravitational force. So if you like, LB, if you are tired of pronouncing that very long word, you can just say weight. Let's see, you can just say weight. So it doesn't matter whether you say gravitational force or you can say weight. The symbol for gravitational force is that one of Fg, indicating that this is force as a result of gravity. Then for weight is just W. So that means the force which is as a result of gravity, the formula is equals to mg. But because we said gravitational force and weight is the same thing, it means also weight is equals to mg. Most importantly, the main influence is that gravity over there. So both of these actually is the same thing. So force of gravity and weight is the same thing, which is as a result of the mass of an object and gravitational acceleration. So number two, let's see, we've got what we call a normal force. We can just say we've got what we call a normal force. And again, normal force is represented by, let me just write there. If you like, you can say Fn. It means normal force. Otherwise, you can just say N, capital letter N. Most importantly, both of these, they are measured in newtons. Why? Because this is a type of a force called normal force. The third one, let's talk about frictional force. So we also have frictional force. So frictional force, normally you can just say capital letter F and small letter f over there. Or otherwise, if you like, you can just make that type of F, which indicates this is a frictional force. Number 4, let's talk about applied force. So for now, LB, you just need to be aware that we've got different types of forces, and here I'm giving you a list of different types of forces. When we deal with those exam type of questions, that's when you will understand better in terms of which type of a force act in which direction, and how does it influence the motion of an object. Force number 4, let's talk about applied force. Applied force, you can just write capital letter F, then A over there. A to indicate this is applied force. Forward slash, if you like, you can just say F. It indicates that there we are talking about applied force. Number 5, the other type of a force is tension. Let's say tension. So with regards to tension, you can just indicate it by capital letter T, or otherwise, if you like, you can say force of tension. Very, very much important, LB. So let's check something very, very interesting over there. Remember, we've got these two types of formulas which says force, it's actually equals to mass times G. Or this formula can be written as force is equals to mass times acceleration. LB, unmute your mic. I want us to now have a quick chat with regards to those two formulas.
Yeah, my mic is unmuted.
Okay, so do you have an idea of why would we have a force being equals to mg and again still have force equals to ma? Are you able to notice the difference between those two?
No.
Okay, so remember, this one is only for vertical movement. I'm sure you now have an idea, ne?
Yeah.
Vertical, let's say, movement. Do you just want to guess or just make a comment in terms of what you understand with regards to that vertical movement?
Does it have to do with the like the vertical component?
So in short, let me just quickly get another board to explain this. So in short, LB, if we have F is equals to mg, so it's actually, when we say vertical movement, it's because of that gravity. We know that always that gravity is, the gravity is always downwards at 9.8 meters per second squared. Do you agree?
Yes, sir.
So again, if you have an object moving sideways, can you see that in this case, that has got no impact on the sideway movement? So that is why in this case we would say m multiplied by a being acceleration. I'm not sure if it now makes sense.
Wait, you're saying that we're using acceleration because gravity doesn't apply there?
In case if let's say this is the floor, and then let's say we've got a car there. Can you see this car is actually moving either to the left or to the right, isn't it?
Yes.
So in this case, this is you in your car, LB. You are driving in that direction and you step on accelerator, and then you start an acceleration, or you start to accelerate. So that acceleration is this one for A, because the one for G is actually for if an object is falling.
That makes sense.
So yeah, so that means always when you see this formula, it means you must be dealing with objects moving up and down, and that G is constant at 9.8 meters per second. But for objects moving left and right, we no longer concentrate on G, because the force as a result of gravity, which is that downwards, is being balanced by the normal force. So they cancel each other out. We no longer talk about those, but we focus on the sideway movement. And on the sideway movement, that's when we have the forces being equals to MA. I hope that one, it makes sense, Alb, isn't it?
Yes.
So quickly, let me also explain something over there to say we have an object on a horizontal slope. Let's say is that car again. I just want you to be aware in terms of how these forces balance with each other. So remember, force number one, we talked about gravitational force. So gravitational force is that one of the downwards force. Let's say force of gravity, then this is mg. Then this force is being balanced by the normal force. And normal force, we say it is also equals to mg. So whatever the mass of the object with its g, if we find maybe the force of gravity, let's say being 20 Newton, because this object is actually on that surface and it's not continuing to move downwards. So that means for it to actually remain in that position on that surface is because it is balanced by that normal force. Let's say this is an object which is not moving, but it is just standing there. So because it is standing there, it's not moving. One thing for sure, we know for it to stand on the surface is because of force of gravity. And for it not to continue a, a falling or maybe sagging this surface is because this surface is actually balancing that object to remain in its position. So it's because of the force normal. So that means the moment we talk about force of gravity, at the same time, you should think about a normal force.
Yes, sir.
Now, let's talk about force applied. Let's talk about force applied. So in that case, LB, does it now make sense in terms of the formula being A, not S, G? So that means G and that one, it's actually both of these are acceleration, but this is acceleration due to gravity, which is constant. And this one, it depends by how much of speed you are driving at, or by how much of speed you increase. Do you have light now, LB, with those two?
Yes, sir.
Okay, so now we also have this force applied. A, a, it it can be cancelled by what we call a force of friction. So force of friction, LB, is the force that is always opposing the movement of the object. I'm not sure, LB, if that part makes sense, but it has to make sense. Before I continue with my explanation, just make sure that that part that I've just explained, LB, it makes sense. If it doesn't, I'll need to explain it, because this is one of the most important forces that you need to fully understand. Does it make sense, LB, with me saying a frictional force is the force always in the opposite direction of the movement of the object?
Yeah, I understand that part, but why do we say that it's opposes the movement of an object? Because of the surface is not flat, or what?
So that means, let's say, if the surface is it's smooth, let's say we have a smooth surface. No, let me start with this one, LB, just so that you've got an idea now. Let's say we have a ice surface, ice surface, and then let's say what type of a surface? Let me just say rough or a bit, yeah, let me just say rough and do that. And maybe let me say a gravel and do that. So obviously, LB, if maybe there's a car or an object traveling or driving on an ice surface which is frictionless. Frictionless. So it simply means this object can move in that direction without stopping. Let's say you just push it in LB because the surface is frictionless. This thing, it can pass provinces, countries, um, what is it, continents, and around the world. Why? Because there's no frictional force. It's more like there's no any force opposing that object. I'm not sure, LB, if you understand that. I'm just trying to explain in terms of these three types of surfaces, meaning that one, there's no friction, which means this object, it will forever move in that direction if it is pushed in that let's say you push it and then it moves at 30 meters per second. So that means for every a second it travels 30 meters and it will be at that speed forever. It will never stop, it will never increase its velocity, it will just travel at 30 meters per second. Why? Because what is it, there is no frictional force. I'm not sure if that part makes sense, LB.
Yeah, it makes sense.
So let's now have a look at a rough surface. You push it again at a speed of 30 meters per second. But because the surface is rough, that means there's definitely going to be a force of friction. Why arrow in that direction is because the movement of the object is in that direction. So that means an object has to first move. Then after a movement has been started, it means that's when there's going to be a frictional force. And frictional force, for it to be there, it depends on the surface being rough or frictionless. Makes sense now, LB?
Yes, sir.
So let's get to the gravel. So obviously, this one being rough, let's consider that to be tar road. You know tar road, Mos? Skontiri. Ne?
Yes.
So also this one traveling in that direction at 30 meters per second. So can you see, LB, that between these two surfaces, obviously this is too rough than that one, and this is too rough than that one, because this one is almost or completely frictionless. This one is tar road, it's a bit rough, but not that much. But when it comes to gravel, it's way too rough. Meaning, for example, this one, it will just travel in that direction forever. Let me do that forever. But this one, because there is a, a rough surface there, as a result of frictional force, this object can possibly maybe travel, and maybe stop somewhere there if it doesn't continue to accelerate and it decelerates. Then for this one, because it's
So you're
gravel,
cutting here.
is it still it's cutting? Let me do this cutting network sickness timeless and whatever. Okay, so is it better now or is it still cutting?
Yeah, it's better now.
Okay, 100%. So let's see. So I was saying in this case, there's obviously going to be frictional force. Also there is frictional force. So there, frictional force is actually equals to 0. So LB, here comes a question. What determines the amount of frictional force. It's obviously because of the surface. You remember we said if the formula for frictional force is actually a what is it, mg. Do you still remember this part?
Yes, sir. So
So because we said the frictional force, it's actually equals to a what is it, mg. Let me quickly check something here on my notes. I just want to make sure that I get that word correct. I'm not sure, LB, if you remember this thing that they call mu. I'm not sure if they do this thing in class. Mu, LB.
yeah, the coefficient.
Yes, the kinetic coefficient. So this is what we call the kinetic coefficient. So we consider this object which is moving, but on that rough surface. So they will most probably give you the coefficient of that surface, and then you know the mass of the object, then you know g. So this formula, it helps you to determine the force of what is it, force of friction. But if it's just F being equals to mg, then this is force as a result of gravity. But the moment you put in this one, then it means you are now converting it from normal force or force of gravity to knowing the frictional force over there. So are you now having an idea, Elbo, of how to interpret those different types of forces?
Yes, sir.
Okay, so quickly, let me do this. Let me say the moment we start having two objects being connected by some, which could be a rope of negligible mass, then that's when we talk about tension over there. So let's say we've got cut A and we also have cut B. So the movement of this is in that direction, LB. Let's try to draw force diagram separating or force diagram for each of this cut. Um, it seems, LB, it seems like because everything is moving in that direction, if you draw cut A over there, it seems like as a result of tension, this cut A is actually being pulled. Um, what is it? Wait. Let me quickly get something there. So this is the tricky part with regards to tension. Firstly, in order to know the arrows, firstly draw both of them separately. Have this one and also draw that over there. So let's see, LB. In terms of this forces acting, that tension, can you see? It's more like this could be because the system is moving in that direction. It's more like this card B is the one which is actually pulling that one in that direction. At the same time, this one is actually pulling towards itself. So it's more like when we talk about tension, we talk about force pulling towards an object. So, for example, it means there you've got that force in that direction, that force in that direction. So that means here we actually have negative tension, and then here we have positive um, tension. Why positive? Because maybe that's if we assume the right direction to be positive. So that means anything in the opposite is negative. Let's maybe have a look at an helicopter there with that over there. So let's see, this is that cable of negligible mass. We've got a container there. Then it seems like there obviously we've got a tension. So when we talk about tension, it's more like we have arrows towards each object. It's more like we have arrows towards each object. I think I'm getting the best explanation of what a tension actually means. I'm not sure, LB, if it makes sense in terms of when you talk about the tension, we talk about two objects being connected by something, and within that string, we have this force towards that, and again, we have that in that direction. I'll also double check if this is a conclusive statement, but for now, let's just say if we have two objects like that, in terms of tension, this one is pulling towards itself, and this also is also pulling towards itself. Can we just conclude on that for now, LB?
Yes, sir.
Okay, 100%. So now let's quickly try to solve those problems. I'm not going to erase this. So what I'm going to try to do, LB, I want to try and bring this question paper. I'm just praying that you'll be able to see this one. Let me quickly do this. I'm just not sure if you'll be able to see because I haven't done this before. Just to avoid you having to try and go back and check in. Are you able to see there, LB? Is it clear? Or maybe if it's small, let me do this and then enlarge that part there. LB, can you see there? Is it clear?
Yes, sir. I'm able to see.
Is it 100%?
Yes, sir.
Okay, nice. So, what I'm going to be doing there is to quickly read through that question. So, normally, LB, with this type of lessons, we normally do this type of a problem so that um, you can also look for similar types of problem. And the other thing, LB, never, ever, ever solve a question paper where you don't have a memo. Name. Um, just just try to avoid that. It could be textbook, it could be a past question paper. For as long as it doesn't have a memo, it's going to make you to keep on wondering if whatever that you did was correct. And again, you will always be convinced that whatever that you did is correct, because you haven't got any confidence and you can just only rely on the information that you have. So always, even myself, when I do this type of question papers, I do prepare for our lesson. I try to redo it and then I check the memo. If I've got it correctly, then I'm going to be able to provide the best lesson to make you understand. So I'm less confident if I have to explain something that I haven't done. And again, having to explain something that you are not sure of. You can even feel that there's no confidence. So the lesson won't be enjoyable. So every time, LB, just make sure that whatever that you do, you've got a memo so that you can always refer and check where you went wrong, how it's being done correctly. So even myself at this stage, um, I still get some questions wrong. It's not like all the questions I'm getting them correct, but I just make sure that for those that I do in the lesson, I practice before. That do you understand what I'm trying to say there, LB?
Yes, sir.
Okay, so quickly, let's see. Question number 4, start a question on a new page. Always, LB, make sure to start each question on a new page. So, 2 blocks of mass 8 kg and 4 kg, respectively, are joined with an inelastic string of negligible mass. The string runs over a frictionless pulley. The 8 kg block is on a horizontal surface, while the 4 kg block is on an inclined surface or plane of a 40-degree angle with the horizontal. The coefficient of kinetic friction um, for both blocks is 0.2. The 4 kg block accelerates down the slope. Okay, let me just quickly try to redraw that diagram over there. So we've got something similar to that, and it forms an angle of 40 degrees there. Then we have a pulley there, then we have that, then we have that bigger one being 8 kg, and then we have this one being 4 kg. That one is a smaller one there. So they said the kinetic friction for both. So you can just say mu k for this one is 0.2, and also mu k for this one is 0.2. So in your head, LB, you notice that that surface is actually the same throughout, isn't it? So if it was different values there, it could mean there maybe it's tar road, and there that portion of that section is gravel. That could be the reason why you possibly have different mu there and there, or a kinetic friction. Do you have an idea there, LB? Does it make sense there?
Wait, can you explain again?
So that means, let me firstly think about something quickly. Okay, let's say we've got a mountain there. Let me get another marker. Let's say we've got a mountain, LB. We've got a mountain, and then there's that other side of the mountain, and this other side. So let's say it's only a tar road at the top of a mountain. It's a tar road there. But down the mountain at that slope, it's not a tar road, but they just left it to be gravel because it's on a slope. Nah. You are driving a car there, and then this car is being pulled by another car. So let's say there's another car. So can you see? Because this one is there, between there, it's actually, what is it? Tar road. And then this one, that section is traveling on, let's say, a gravel there. So obviously, the coefficient of friction there, maybe it could be 0.2. It doesn't matter whatever that it is. But there, it could be 0.3. Why are these coefficients different, LB?
Because of the surface, it's not the same.
100%. So my question there was, what can you say about these two values being the same, the coefficient of friction?
Wait, does it mean that it has the same surface?
So we can just assume that the surface is the same. Nah.
Yes, sir.
Okay, 100%. So let's see. Let's try to check what the first question. So the first question, we can just keep it most, because that one, it doesn't change, isn't it? I'm not
Yes.
sure. Are you able to see that question?
Yeah, state Newton's second law of motion in
Yes, yes. So we can just skip that one. Let's go to 4.2, which says draw a labeled free body diagram of all the forces acting on the 4 kg block. You remember, LB, that we've got two things. What we have? We have a labeled free body diagram, and we also have a labeled force diagram. Do you remember, LB?
Yes, sir.
So in this case, you would notice that what they actually want us to calculate is a free body diagram name. And remember, free body diagram for the 4 kg. So the 4 kg is that one on an incline. So remember, you first make a dot. Why a dot? Because it's a free body diagram. So what are we having there, LB? What type of forces are we having there? Let's check. Did they ever talk about applied force in that statement?
No.
No. I don't remember. So that means number 4 is out. We know this one is always there, isn't it?
Yes, sir.
And then obviously because this one is there, we know this one is there. It has to be there. Normal force is always there, especially if there's a surface. So if there's a surface involved, LB, if there's a surface involved, then normal force is there. But if an object is hanging, for example, an helicopter which is trying to pull a load towards itself, can you see this object is actually hanging? It's not on a surface. Do you agree?
Yeah, so it means that there's no normal force.
There's no normal force for that reason. But because here we're dealing with an object on a surface, then normal force is there. So you can see these forces are actually in order, LB. That one is always there. This one, it depends if an object is on air or otherwise on the surface. So frictional force also, it depends on the given statement, whether they say there's coefficient of friction or maybe they say the surface is rough. For that reason, we know frictional force is to be there. LB, in this case, you said there's no applied force. Then we can just scratch it out. So do we possibly have a tension? Or did they say there is tension?
I don't remember, but then since it's hanging, means that there is tension.
So let's say because it's connected. Let's say because it's connected. Nah.
Yes, sir.
Because obviously in terms of hanging, that's when we talk about an object which is in the air. So can you see that one is connected? Nah.
Yes, sir.
Yeah. So that means how many forces do we actually have? It seems like we've got 4 forces, isn't it?
Yes, sir.
So obviously we know weight is always in that direction. So we can just start with weight, and then normal force, it's always perpendicular to the surface, because you've noticed that every time when you talk about normal force, we talk about the surface. So it's always perpendicular to the surface. So can you see that surface is at an angle? That is why the normal force is going to be in that direction. Very, very much important there, LB. Now, can you see? We obviously have that one of tension in that
Wait,
direction. So you can
sir.
just write it. Mm-hmm.
Wait, how do we estimate the direction of the normal force? Like where to put it?
So let's say we've got an object on that slope. This is that. So always when you do the direction for the normal force, it's always perpendicular to the surface. Can you see there's the surface? It has to form a 90-degree angle there. So that is why we say it's in that direction for this slope. So if it's on a horizontal slope, if you draw a perpendicular line, it's going to be in that direction because you need 90-degree angle there. So that is why your normal force is in that direction. And then for this slope also, it is going to be, let's say you've got that object there. You need that 90-degree angle there. I'm not sure if it makes sense now, LB.
Yeah, it makes sense. Thank you.
Okay, 100%. So let me remove all of that. Then you remember, because they talked about the kinetic friction, what, which means we are going to have frictional force. Can you see?
Yes, sir.
So this is how you easily draw a free body diagram for that 4 kg block. I hope that one, it makes sense, isn't it?
Yeah, it makes sense.
So can you see now? They want you to calculate the frictional force between the surface and the 4 kg block. So frictional force is exactly what the question wants you to calculate, LB. What do you know about the frictional force? You know that the frictional force is actually equals to mg. But if there's a surface which has got a kinetic or a coefficient, what do they call that? let's see, if it has a coefficient of kinetic of friction, then that's when that formula you edit mu k there. So you can easily substitute that. You can just punch on a calculator. I think this is 0.2. What is the mass? Which object? We are talking about the 4 kg object over there. What is let's see, what is
9 point something 8.
Okay, 9.8. But there's something that I want us to be careful of. Let me just quickly check also on the memo there. I want to confirm something. So I noticed something there. Remember, this is actually on an incline. It's actually on an incline. And for that reason, that is why we add cos angle there. I'm not sure if you remember this formula, LB.
I never really understood it, to be honest.
So let me try to remove all of that. I hope I might be able to explain this one. So let's see, if we have an object on a horizontal surface similar to that, and then we have this. So if you have the weight there, we know force of gravity is equals to mg. Then we know the normal force is actually going to be Fn, which is equals to mg over there. So always, for the sake of making it easy, LB, let me quickly check something there. Let me see. I will tell you just now, LB. Okay, so for this vertical forces, it's actually let's see, sine angle. And also for this one, we can just say it's sine angle there. So for the vertical movements, we add sine angle. What is that angle? We said normal force acts at 90-degree angle, you remember, and this one always is vertically downwards. So that means also at 90-degree angle there. So that is why we also have a sine 90 there. But for objects in that direction or parallel to the surface, that means for force of friction there, we might possibly be having, let's say, that mu, then mg, and then for this one is cos angle. And then in that direction, that's when we can be having applied force, or if not applied force, tension. And again, in that direction, we can also have tension if the objects are actually that let's see, we have tension, it's going to be there, cos of angle there. And the reason for these formulas to look like that, let me do this. Let's say for an object similar to that one, it's on an inclined surface. Let me do this. So it's on an inclined surface being a 4 kg. So you remember, LB, that the weight is actually vertically downwards. But this object, as it accelerates downwards, as they say from the statement, do you agree that this object is not actually moving in that direction, but it's moving in that direction? Do you agree?
Yes, sir.
So that means this is the component of that Fg. So this component, it is the one where we say this is actually Fg. What was it? I think this is the one which is Fg cos angle. And then this one is the one which we say is a Fg sine angle, which means also force normal, remember, is balanced by that, and it's not balancing this one because force normal acts perpendicular to the surface. So that is why even for force normal we are having a force of gravity, what is it sine angle over there. I'll just need to quickly confirm something. Let me just quickly confirm something, LB. I just want to check in terms of those trig ratios whether it's sine or it's cos. I'll just quickly get it from the notes there. Yeah, no, I got it. I got it there. It is actually cos and sine. Let me do this and say cos angle, sine angle. Remember, the reason to that is because there is a triangle with an angle being theta there. In that case, it's going to be that 40 there. So that means if we complete a triangle there, this is that triangle we are having where there's 90 degrees there, and that angle is actually there. So we try to come up with trig ratios for these components where we know this being hypotenuse. I think I've experienced load shedding on my side. LB, just make sure that in case if it starts to disconnect, then just know that possibly it's a network, but I've got some light over there. Are you still able to see and can you still hear me on your side?
Yes, sir.
Okay, so let's try to push up to wherever we can. But what I'm trying to explain here, I wanted to say we have weight in that direction. So we want to resolve the components of that weight. So we have to have a right angled triangle. So can you see with the angle? Let me see. I just need to be careful in terms of exactly where that angle is because it could be there or it could be there. So I just need to make sure of that one. Let me also see there on my notes. I'll confirm for you that one shortly, LB. Yeah, I think with the first one I was right. Yes, I was right. So the angle is there indeed, but now is this the adjacent side or is between these sides, LB? Which one is adjacent?
The one next to FG.
This is the adjacent one, eh?
Yes,
And
sir.
and which trig ratio is associated with adjacent?
Cos.
So that is why there we are going to have FG cos of this angle, which is the same as that angle. And this one here, obviously, it's going to be FG, what is it, sine, because sine is the trig ratio associated with opposite, isn't it?
Yes, sir.
So can you see? This is the force in that direction, which is actually that force. This is the opposite, and then this is that one. So that's why there we actually have sine angle there. So can you see that diagram that I drew over there to say, what did I say? I just want to make sure that I've got it correctly there. So that means for this sideway movements, that's where we have sine, and then for this ones, that's where we have a cos. So there it means it is supposed to be sine if it's that one. I just want to make sure that I'm getting it correctly there. Let's say sine angle, and then again where you see now that diagram is losing me. Let me quickly try to redo it, LB. I think it will form part of an additional explanation to what I've just explained. So let me maybe also draw it in a different angle to say we have an object there. Let's start with the weight. and there we've got angle theta there. So what I was saying there, LB, is to say in terms of the weight of this object is always downwards. So let's say from the center there, downwards. I think I'm running out of ink there. It's always downwards. But this object, LB, it's not moving in the downwards direction, but it is actually moving in that direction there. And again, in terms of the force normal, we said it is a perpendicular to the surface, which is at an angle. So that is why there we are having another component of the weight there. So this is FGLB, or otherwise it is the weight. But the forces acting on this object are actually the components of this weight, because this object is not falling in that direction but in that direction. So that actually means what we can therefore do is to have this line, we just bring it down there. Why there? To form a right angled triangle. So that angle is actually there. So now can you see, LB, this is what you said. You said there we are going to have FG because it's cos, then we are having cos angle there. And then for this one, which is the same as that one because it's the opposite, then this one is FG sine of angle, being that same angle, being that same angle. I'm not sure if it now makes sense, LB.
Wait, so isn't the FG, no, isn't cos theta like perpendicular to the component of FG? Like,
Let's see. Wait, you're saying isn't FG what?
cos theta is the component of FG perpendicular to the surface.
So you're saying isn't FG cos theta perpendicular to? Yes, it's wait, I'm failing to understand your question, LB. But before you ask it again, let me just try to re-explain. Then maybe you'll try to ask it differently. So let's see. We have the weight in the downwards direction, yes, so we call it FG. But this object is not acting the same direction as that, which means we've got what we call the components. We have that first component, and this is the second component. So we have an angle over there, then we form a 90-degree angle there. So we just need to know, because this is now our what is it? This is our hypotenuse. So we have hypotenuse, we want to derive that adjacent side. So can you see? This is the angle, this is the right angle, then this is the one which is a cos angle. And then this one is opposite to that angle. That is why we are having sine angle there, which means a force of gravity cos angle is the one which is balancing with the force normal, which is perpendicular to that component. So that means there we actually have force of gravity, or mg, cos of angle. And then for this one is force of gravity sine angle. Yes. Now you can ask a question, LB.
No, so it's fine.
It makes perfect sense now, ne?
Wait, so which means that we're using sine theta to calculate the horizontal surface.
So that means if we calculate a force in either that direction or this direction, which could be the frictional force, then is the one with what is it, sine angle. But remember, in this case, what we are calculating is the frictional force, and we said the frictional force is actually equals to mg. It's actually equals to mg. But remember, because it's on an incline, then we have to say cos of angle. And again,
Makes sense.
because And again, because there is that surface with a coefficient, whatever, then we add that coefficient there. Then this means this is the formula for calculating the frictional force on an inclined surface. So if it's not on an inclined surface, it means there's no angle there. But anyway, if you want to put in an angle there, let me just quickly check something there. I was just trying to test an angle there. So let's see. Can you see if it's on an incline, then it's cos whatever angle it forms. But if it's not on an incline, it's just mg. If there's that, then you also insert that. Makes sense, nay?
Yes, sir.
Okay, 100%. So let me see. Can I can, oh, so this lesson is being recorded, LB. As soon as I'm done, I'm going to send it to you via inbox. Name. Just remind me on that one. The other thing, okay, let's proceed with that question. I think, what will we do with the LB? I think we're still trying to calculate that question. Can you still able to see the question paper there?
Yes.
And you say it's clear, ne? Let me try to do this and check. No, it seems to be 100%. It seems to be 100% clear there. Okay, so let's see. There it says, where are we? Calculate the frictional force between the surface and the 4 kg. This is where we are, LB. So, obviously, we said force of friction is equals to mg, first thing first. You agree there, isn't it?
Yes, sir.
And this is actually force normal. And again, this is actually force of gravity. You agree there, isn't it?
Wait, why are we adding those two?
No, I'm just saying this formula is for force normal and again is for force gravity. It's the same thing.
Yes, sir.
So because this object is on an incline, the 4 kg object is on an incline, 4 kg is on an incline, then we add cos angle. Now you know where that cos angle is coming from, isn't it?
Yes, sir.
And because they've specified to say that surface has got a coefficient of friction of 0.2, then it means on our formula we are going to add that mu. Do you agree?
Yes, sir.
So that means, LB, if you are given a question for a surface there, if they say force of friction, you know force of friction is mg, first thing first. Is it on an incline?
Yes.
So this one, LB, is not on an incline.
Oh, sir, I didn't hear your question. I thought you were talking about the other one.
Oh, no. This one, let's say B. It's not on an incline. There you agree and you understand, ne?
Yes, it's not on
So
the
that
incline.
means we don't need that cos angle, ne?
Yes, sir.
So in terms of this, LB, it depends if it is given on the question or not. Sometimes they might say this is the frictional force, and then they want you to calculate that coefficient, whatever. If they want you to, or they talk about it, just know is there, and it's either they will give it to you or they will want you to calculate it. If they want you to calculate it, then you must be given that force. Does it make sense now?
Yes, it makes sense.
So can you see, LB, sometimes we don't really need to do all the questions related to this type. We just do that one question and we explore a lot of information out of that one problem. Then from there, we move on to other types of problem, just so that you've got exposure. Because obviously a question won't come in the same way, but you just need to be aware of important information. So don't worry that much in case if for this chapter we may be dealing with that type of a problem. We know we have discovered a lot there. It's only when you practice on yourself with something that has got a memo, especially in terms of the calculations. Then on our next lesson, you can just indicate to say, maybe quickly have a look at this and everything. Makes sense, ne?
Yes, sir.
Okay, so let's say FG is actually that mg cos of angle. So let's say this is the general formula. It all depends on what we have. So we do have this thing which is 0,2. We have 4 kg. We have 9.8. We have cos of 40 degrees. So whatever that we get is the frictional force. And most importantly, LB, make sure that your mass is always in kilograms. Nah. Let's
Yes.
make sure of that. So what is that?
Wait, let me quickly calculate.
Okay. 0,2 multiplied by 4 times 9.8 times cos of 40. Hey, I'm getting something there. I'm not sure if you're also getting the same answer.
6,0057.
Yeah, so it's more like we can just conclude to say frictional force is actually 6 Newton because it's a force. So it's 6 Newton. Ne.
Yes, sir.
So did it make perfect sense there? Let me say 005. Okay, let's say 0.01 there because we can round off that to the nearest whatever. So we can just say it is actually that. In which direction is the slope? Is it downwards or is it up the slope? Is it down the slope or up the slope?
Up the slope.
Why up the slope?
Wait. I don't know how to explain.
Okay, so every time when I ask you in which direction is the frictional force, ask me this question: in which direction is the object moving? Make sense?
Okay, yes.
So do you believe I'm going to tell you in which direction the object is moving? Can you guess what I'm going to say if you ask me that question?
To the right. I don't know.
No. So in short, I'm saying
Downwards.
if I say in which direction is the frictional force acting, and you ask me in which direction is that object moving, I won't tell you in which direction. I'm going to say refer to the given statement. So that means in the statement you should be told in which direction the movement of that object is. Make sense? Because obviously when you write exam, I won't be there to answer that question. So I just want to guide you in terms of where you get that information. Happy there?
Wait, says so. When we calculate, we have to also mention the direction.
And again, tell me why are we supposed to mention the direction?
Because they want to know where the frictional force is acting.
So it's because force is a vector quantity and not a scalar quantity. So the difference between the two is because, for example, time, you can only say 2 seconds. There's no direction there. Mass is 4 kg. There's no direction there. But when it comes to force being a vector, you give the magnitude and also the direction to say up the slope. Make sense?
Yes, sir.
100%. So quickly, let's try. Let's try to move to the next question. So one thing for sure, I think we'll end it there on this question. Now, our next lesson, I think, because I've given you a bit of a background, then we can run through those two questions. I'll add another type of a problem. So this is the first type of a problem that I wanted us to look at. The other type LB is this one. I also want to take you through this type. The other type is this one. I also want to take you through this one. Then from there, the last one that we're going to do is this type, but without that 8 kg. You just have one either in that direction or in that direction. I think there we'll say will be sorted with those type of calculations. Because I see
Yes.
on the same question paper, you can see this type is given, this type is given, then also this type is given. So I think if we can try to cover all, then you'll have an idea there. Let's see. That last question says calculate the magnitude of the acceleration of the system. So this one, they are actually talking about the system there. The system is both of these things. This one of 8 kg, and again this one of 4 kg there. So let's see. You remember that we have this negative t in that direction LB. Wait. I just want to confirm something. So that's actually what I wanted to confirm. Let me just check on the notes. So just like with those forces there, to say this one is in that force and this one is in that force, I also want to confirm when it comes to tension there. I'll let you know shortly. Remember, LB, before I finish with this lesson, I will still need us to have that quick discussion there, just to check if it could be something which might work for us. Let me see, LB. Let me see. Of course, tension being number 5. So I just want to confirm quickly with regards to those arrows there. I want to make a conclusive statement such that always you know that the force in this, if the tension is in this, let me see. Okay, no, it's fine. I think I'll just have to try and actually let me see. No, LB, I think with this one, I'll try to make that conclusive statement separately. But for now, let's do the calculation. So what I wanted to do, I wanted to check if I can conclude to say, for example, with that one of forces, we said for the one along the surface, these are the ones with what was it? I think it was sine. Yeah, it was sine. These are the ones with sine angle, and these ones are the ones with cos angle. And I explained why. So I wanted to check also with this tension if I can possibly conclude with the arrows. But let's see. If we separate these two, then we end up having this one of the 8 kg with a string in which direction? With a string in that direction, LB. And also we have this one of the 4 kg in which direction? In that direction. So it's more like this object is actually being pulled in that direction by that object. And at the same time, this object is more like it's actually being pulled in that direction by that object. I'm not sure if it now makes sense, LB.
Wait, can you please repeat that again?
Okay, so when we look at this object alone, as a result of that cable, do you think in which direction is this cable pulling this 8 kg?
You're saying the cable, you're asking the cable is pulling what?
Let's say maybe we have a string, and let me say, how do I ask this question, Abe? So I just want, obviously we disconnected these two objects. So I'm saying this string or this rope, does it not seem like it's pulling this object in that direction? Because remember, on the statement they said the system is, or this 4 kg is accelerating down the slope. And for that reason that this object is actually moving down the slope, down the slope, it means this string or this cable is actually pulling, the 8 kg in that direction. So that is why I'm having that arrow in that direction there.
Okay, yeah, it makes sense.
And again, with regards to the 4 kg, that's what I'm saying. It seems like the 4 kg, because of this string, it's actually being pulled in that direction by that 8 kg there.
Yeah, it
So
makes sense.
So when I was trying to talk about a conclusive statement, is because I wanted to say, always when you have two strings, let's say you have a string in between and you have two objects, a conclusive statement that I wanted to make is that if you have a rope in between, when we talk about a tension, we talk about an arrow in that direction and again another arrow in that direction, meaning this arrow is for this object A and this arrow is for this object B, which means the tension in the rope is actually for this object in that direction, for this object in that direction. So it's more like tension, it's a force from object. So can you see? This is the force away from the object. This is the force away from the object. So I wanted to check if I can conclude to say always when you have a tension. For example, let's say you have an aeroplane there, there's that. So what I mean by that, this is a container. What I mean by that, it means force away and again force away. So that's what I wanted to say. This is the tension of the helicopter and this is the tension of the container. That's what I wanted to check when I was having a look there, to say this object is more like it's being pulled towards the top, and at the same time this object is more like it's being pulled downwards by that. I'm not sure if you now understand what I was trying to do there, LB.
Yeah, it makes sense.
Okay, 100%. So now let me remove all of these, and then from there it's just a matter of formulating. We formulate everything regarding the 8 kg. We do the same for that. So that means tension of the 8 kg is equals to tension of the 4 kg. Why? Because these are the forces inside the same string. Does it make sense? So that means
Yes,
if you
sir.
have objects like that and in between there's a tension, that means if you have away and away, this is A, this is B, that means tension for object A is actually the same as tension for object B when you separate them and look at them individually. So it's more like a a these two guys, they committed crime together, nay, but when they go to court, this one is going to face his own charges, this one is also going to face his own charges, but they committed the same crime. Does it make sense?
Yes, sir.
Okay, 100%. Now quickly, let's try to formulate. Remember, we said force net. This is a formula which is force net is equals to, what is it? I think it's equals to MA. So always force net is equals to MA. So it's only when you talk about force of G, which is equals to mg. But when you talk about a force, when you equate it to MA, then we say it's force net. So this is a formula. You're not seeing it for the first time.
Yes.
So net, the word net means total or all forces acting on an object. So let's formulate for the 8 kg. So that means how many forces are they acting there? I think is that one of the tension, and again is a force of friction as a result of that 0,2. Do you still remember?
Yes, sir.
So that means we only have two forces acting there. And the first one, let's assume the right to be positive. So that means it's going to be positive tension, and again minus force of friction. Then this is equal to ma. So force of tension, we don't know what that is, but I think we know, LB, what the frictional force is. Did we not calculate it? Let me see.
Yeah, we did it 6,01.
But remember, that one, LB, it was actually for this one on an incline, which is 6,01 Newton. But this one, it's not on an incline. So that is why we have to separately calculate that one as force of friction being a 0,2 times mg and not cos angle. Does it make sense now?
Oh, yeah, it does.
You see, so can you see the tricky part here? If we only think of a force of friction being that, so now you understand what that cos angle means, isn't it?
Yeah.
So that means there we are going to say 0,2 multiplied by 8 multiplied by 9.8 is equals to MA. Then we can just make this the subject of the formula to say it's actually equals to, what is M? M is 8, so it's more like it's 8A. Acceleration, we don't know. Then we transpose, what is that when you punch it on a calculator? 0,2 times 8 times 9.8, it's equals to 15.68. So that means we have plus 15.68. Can you see? So the main aim is to make T the subject of the formula so that we can equate them together. Why equate them together is because we say tension of that is equals to tension of that. So it's the same crime committed. So it's committed by different individuals. So that means their crime is actually equal. It's only that they go to court individually. Make sense?
Yes, sir.
So let's see. Let's formulate for this one. For this one, how many forces are we having there? You remember we have this one of the tension, we also have frictional force, and we also have that component in that direction because they said this thing is actually moving down an incline. So that means force net for this one is going to be equals to MA still. Then what are we having? We have that force in that direction. What is that force? Is mg, was it cos? Yes, we said, yeah, is it sine or cos for this one? I think it's sine.
It's cos.
Is it not sine?
But the second x thing is always associated with cos. And
No,
then
but
y
remember,
is sine.
so remember, it's not that this is the adjacent. Agree? We had that, and then we had these two components. Then we had that there, and we formed 90-degree there. And can you see, we said this is the one which is cos angle, and then this one is the one which is sine angle. So can you see that one is the
But I
one which
say,
is sine
isn't
angle?
that going to apply to only when we're looking for the angle that is like on the surface? Or maybe I'm wrong, I don't know, because
No. So remember, that angle is actually there. So because now we resolve the components, so you have that like that. So that means only when you calculate for force normal, that's when you use cos. Meaning there's no way when you calculate for this component, it can be cos and again still cos. So it is that sign there.
wait, can you please repeat that again?
So you remember when we're calculating the force normal, we used what was it? We used cos. I'm not sure if you remember, LP. We used cos.
Yes.
And the reason for that was because when we resolve the components of this weight, it ends up being that component, and we also have that component forming 90-degree angle there, and the angle being that. So we said this is the one which is associated with cos because it's the adjacent near. Then there's no way also this one can be adjacent. It has to be sine because it's opposite to that angle. That is why there it's actually sine angle. For the forces acting parallel to the surface is sine angle. So the triangle that you're looking at is not this triangle LP. It's not that one, but it's this one.
Okay, it makes sense.
So that means always when you calculate force normal, it is cos angle. But when it comes to either the frictional, so either the tension or maybe that component, is the one which is a sine. So maybe don't be confused because we calculated force friction which is horizontally in that direction, but we used a cos. So the reason to that, we said this vertical force, when we multiply it by that coefficient, or even if we don't multiply it by coefficient, the normal force is actually frictional force. So it's more like we used vertical components, but we know that that same vertical force as a result of weight, it is still the same as the frictional force. But it doesn't mean that because we calculated that using force, then we say it was a horizontal component. It was actually a vertical component that we calculated, but we know it's equals to that force which is in that angle. Make sense?
Yes, sir.
So that means for this component is going to be mg sine angle. So let's now add all the forces acting there. We have this one in that direction, which is positive mg sine of angle. We have those two in the opposite directions. That means we have a force of friction. We also have minus tension. All of this is equals to ma. Does it make sense, that formula?
Wait. Mg is equals to Fg is equals to mg sine theta. Or we're replacing the F net with the mg sine theta.
Oh, okay. No. This is actually force of gravity parallel to the surface. So F net is the total forces. Net means total. So just like we did there, we said only two forces are acting on that object. That's why on force net on that side we had 1, 2. But on this object, how many forces are we having there? We have 1, 2, and 3, which is force of gravity parallel, force of friction, and force of tension. It's equals to ma. I'm not sure if it makes sense there, LB.
Yeah, it makes sense.
So always remember, F net is actually total force. So we look at all the forces acting on that particular object. So this is the one that I actually simplified because we know mg. What is mg? Mg, no, what is it? Fg is mg again. Then what is the sign there?
Say you're cutting, can't hear you.
I think now it could be the network issue now. But let's quickly wrap up. Can you hear me now?
Still cutting.
Is it still cutting? Yeah, no, let me try to quickly check. It could be the network there. Can you hear me now? Is it still cutting?
Yeah.
Yeah, no, I can also hear you from your side. You're still cutting. Let's see. Is it still cutting, LB?
It's still
Okay, but it's fine. Let me try to quickly squeeze something, or let me just write. Maybe you will see. Because if I write, you will now understand. So, mass there, what is the mass there? What is the mass there? We're dealing with the 4 kg, so it's 4 into 9.8. Then we have sine angle being 40. Frictional force is that minus tension is equals to 4a. Are you still there, LB? Can you see that part?
Wait, the formula is confusing. Okay, M net equals to MA. Then we're looking for all the forces, right?
Mm.
Wait, so are you replacing the F net with empty sign theta? Then you're gonna add all the other forces next to it.
Oh, you say you have been confused by that one. Let me do this. So we know that FG parallel is that FG there. It's actually FG minus force of friction minus tension. So remember, for that 4 kg, we have frictional force in that direction. We have tension in that direction. We have a force of gravity parallel to the surface in that direction.
Okay, when do we add the empty sign theta?
The mg sine theta. Okay, we add it because as a result of force of gravity, they said this object is actually moving down the slope.
Yeah, I know. I'm asking where do we put it?
Let me explain to say on the formula, this is mg sine angle, and force of friction is that one we calculated. This is tension. I'm not sure if I'm still not answering you, LB.
Wait, so the empty sign theta is FG parallel, then you replace that with sine
Oh, yeah.
40.
Okay. Let me see. I just want to have some way I can. Okay, let me remove that portion there. So yes, you replace FG parallel. FG parallel, FG parallel, the formula is mg sine angle. Yes, I'm not sure if I've answered you there.
Yeah, it makes sense now.
Yes, so this is FG. Because remember, always when we talk about FG, always we talk about mg. Ne? So because this object is on an incline, then that's when we add sine angle. If it wasn't on an incline, then there's no need for us to add that one there. Makes sense?
Yeah,
So obviously, if there's no this one, then it means it's on a surface. So it is in that direction, and it is in that direction, they cancel each other out. That's why on a formula, you won't even have that, because it's either is force applied or there's tension there.
okay, wait,
So
what does the 4 and the 9.8 represent now?
you mean, what is it, the mg?
No, down there where you are replacing.
So this one, the downwards, that one.
No, say there where you were replacing the FG parallel F force of friction and T and whatnot.
Mm.
The last thing that you wrote.
Wait,
Wait, so
let me see.
I get you're saying FG parallel is for
Mm.
sine 40. What about the
Yes.
4 and the 9.8?
What
Below there
about,
where you're
this
substituting.
day?
Yes.
Oh no. No, I get it. 4, we are dealing with the 4 kg, and then G is 9.8,
So
and
most it's
then
still necessary to write the MG.
yes, it's still necessary. So that is why there I actually didn't have that FG parallel. So I just wrote it as formula as mg sine angle. But what you need to do there, just write it firstly as FG parallel. On your next step, then you can still write it as MG sine angle, but you will still need to then rewrite all of this as they are. Then from there you substitute. So
no, it's
does
fine.
it?
So I'll just use the MG.
Yeah, so you can just use the MG, it's fine. Then from there, can you see what you do is just to punch all of this, then you transpose, isn't it? So you end up having a T is equals to 4A. When you punch all of this, I think it has to give, let me just check there on the memo. It gives you 19.19. What is it? It gives you 19.19, yes. So you end up having to transpose this one to the other side, and this one it gives you 19.19. Then you transpose that one, you have minus 4A there. This is just a math calculation that you can perform. I'm not sure if there it makes sense, Albie.
Yeah, it does.
So can you see? You can easily finish it off because you have this. You just equate it to that. Then you calculate for the acceleration, because that's what the question wanted you to calculate, isn't it?
Wait, can you repeat that again?
So we are trying to calculate the, what is it? What are we trying? So the question wanted us to calculate the acceleration. So we did this, the subject of the formula, so that we can equate it with that. So this is equation number 1. This is equation number 2. So you equate this to that, and then you solve for A. So let me see. It's actually 8A, which is that one, plus 15,68. You equate it to 19,19 minus 4A. Then you can transpose. You have 12A there, which is equals to trans. I'm not sure if I'm losing you there, LB.
Say you are. You're supposed to replace the T with the 19,19 minus 4A.
Which is that one
Where
there?
there is T, we replace with that.
Yes, which is that one there. And then here's another T, which is that one there.
Wait, I was
Mm.
I get we're looking for acceleration, and that side there is no
Yes.
T, like to substitute.
Wait. Let me see. Okay, so this one we are on the same page there, isn't it?
Yes.
Yeah. So we do the same for this one. Then we made T the subject of the formula. I'm not sure if up to here we are on the same page.
Yeah, we are.
So can you see that T for the 8 kg is equals to this, and this T for the 4 kg is equals to this.
Mm-hmm.
Then we know the crime is the same, isn't it?
Yes.
So that is why I equated the crime there.
Okay.
And the reason for that is because I know I've got that A that I can solve, which is going to be acceleration of the system.
It makes sense. I thought you were doing the simultaneous thingy
Yes,
because there's no
it's more
T
like
there to replace, but then so you're just adding them together since they're
yes,
equal.
we make them the subject of the formula, then we equate them because we know it's the same crime but committed by different individuals. So can you see now, there you just solve for A. You transpose, it becomes 12, then that 19.19 minus 15.68, I think there is 3,51. Then A should be equals to that divided, by 12. 0.29. 0.29 meters per second squared. I'm not sure if it makes sense there, LB.
Yeah, it makes sense.
Okay, so quickly, before I run out of battery, let's check if we can quickly have a look at that question. So this one will also just check the memo there in terms of what it says. I'm not sure if you'll be able to see there. But the question says,
So,
how?
say, I have a
Mhm,
question.
mhm.
So, like, when we have like a question that has like two objects acting on it, we have to like calculate them separately, and then if
So,
there's a need for substitution, we have to substitute.
yeah, so it's more like it always depends on the question and also in terms of what the question wants. So can you see in that case, they want acceleration of that system. So you just need to individually sort out the 4 kg, individually sort out the 8 kg, but you know there's something common about those two, which is the tension. So depending on what the question wants, you should just always know that the tension is the same. So you try by all means to find a way in which you can use that to your advantage. I'm not sure if I've tried to answer you there, LB.
Yeah, you did. Because this question has a lot of marks, and sometimes I struggle with it.
It has a lot of marks and sometimes it's tricky, I know. So this question it's a bit tricky. So that's why I'm saying if you can find another one which has a memo, just go through that question, try to see if you can understand. Otherwise, if it gives you a problem, then on our next lesson, you can quickly send me a screenshot of the question and the memo. Then I'll make sure to study it. If I can study it, up to a, a stage where I feel like I'll be able to explain until you understand. Then we'll go through that particular question. As long as it has a memo, so that we don't get chow together.
Yes, sir.
Okay, so the last question says, how will the acceleration compare if the positions of the 8 kg block and a 4 kg block are switched? Choose greater than, less than, or same answer, then explain your answer. But one thing for sure, obviously, this one of 8 kg, it has less mass, therefore its weight is going to be less. That means acceleration is at whatever acceleration it's moving. But the moment you swap, can you see? Now this thing is going to accelerate even more because more weight is on an inclined. Does it make sense?
Wait, can you please repeat that again?
So let me do this one. So can you see? The 8 kg is on a horizontal surface. This one is on an inclined. So this thing is actually moving in that direction because of the weight of this on an incline. According here, it slopes in that direction because of that. But
Yes.
if you replace this mass, if you exchange, you put this one there and you put that one there, can you see now this one is going to be having more mass on an incline, which means it's going to slide even faster because of it has more weight.
Yes.
So does it make sense, that part?
Yeah, it does.
So that means obviously your first response to that question is going to be greater than, for that reason, isn't it?
Yes.
It's greater than. Let's see what reasons they are having there. So obviously greater than, and they say the component parallel to the slope increase. So what they are actually meaning is that mg parallel is going to increase. Why is it increasing? Is because the mass is more now. That is why it is going to increase. I'm not sure if it makes sense there, LB.
Yeah, it does.
And then the next thing, obviously we know tension in the rope, it stays the same. Doesn't matter whether this one is there or that one is there. The crime is the same. That one you should always remember. Ne? And being the same, it means they are equal. Ne?
Yes, sir.
And then now, the force net is obviously going to increase. Because why? Because of that mg parallel has increased. So these are the reasons that you can give in response to that question. So I'm not sure before I close this lesson, LB, if you've got a question.
No, I don't. And you like I
No.
should remind you of something.
Yes. So that's what I wanted us to actually discuss. I want to check if it could work to our advantage. Because let me now check something. Let me quickly check something there. I want to check in terms of how long we have spent. Can you see almost 2 hours, but we did only one question. Let's say almost 2 hours, but we did only one question. So I'm realizing as I do these lessons to say, I've done it with the other learner. I think in 1 hour we managed to cover, let's say, a bit of intro. Let me say a bit of intro, and again we did a 1Q paper, and then the second one we just browsed it through. I just want to check if it can also work for us. So what I did there, LB, was that, for example, you see on this lesson that we did, I let's say I did live presentation of the intro for that chapter, ne? And then again, I did a live while going through that question paper, and then again the other thing that I did, it was to go live still answering the questions, ne? So my question was, would it work if we give it? Obviously, I think I can propose that we give it a try, ne? Such that, let's say for this same question, what I do before we start with our lesson, I just record explaining everything. That means separately, I'm going to have a record that summarizes that introduction. Because one thing for sure, you see, especially that part of a conclusive statement in terms of the tension and also the trig ratios on an angle and what. If I do a pre-recorded lesson where I do an introduction of that, I know in 20 minutes, for example, I can cover everything there. Then I take 5 minutes interpreting, let's say, whatever question paper that we'll be doing. Then from there, I can still spend, let's say, 20 minutes trying to solve that question paper. So in that recorded video, it will be something similar to that, where on the screen, whatever I'm doing now, I play that recorded lesson. It's explaining and everything. Where you don't understand, then I can pause it. You ask the questions, then I explain. So in addition to that, you might find that interaction, maybe it adds up to what is it, another 10 minutes. So can you see, if maybe we do it, let's say for a total, or maybe let's say a total of 40 minutes, an additional 20 minutes, maybe to make it an hour, no, another 30, let's say an additional 30 minutes, or 15 plus 15, we can still cover 2 more questions, because I've given the theory there. I've also interpreted the questions there, and then this time is spent on us solving the questions. Where you don't understand, I just pause, and then bring a what is it, a video, or I just bring a screen that shows you this part where I'll be explaining and everything. Or otherwise, I can still do it online on the screen on the question paper. It will obviously depend on how your question is. So also this thing, LB, I think the advantage to it is that we can do more problems for the same chapter. And again, in case if, let's say for example, in case if you'll be writing on Thursday, because I still have all of that information recorded, then if you would propose that we shift that lesson, instead of being on a weekend, then we shift it to, let's say, day before, we can easily redo exactly what we did, because I'll still be having that same information which is summarized. Then I just play, then we just discuss it or go through that information. I'm not sure, LB, if you understand what I'm trying to say there, if you are open to give it a try.
Yeah, so you can just give it a try and see
Yeah,
if
so
it's going
let's
to work out or
yeah,
not.
so let's see if it's going to work or not. I'm also thinking of introducing the same for those Monday to Friday lessons, because I noticed that in case if I happen to be sick and I'm not able to do lessons, can you see that everything is going to completely stop? So that means all the learners for one-on-one is going to stop. Monday to Friday lessons also, they're going to stop. But if I do it this way, then um, even if maybe, for example, there's another learner who wants one-on-one, I can still redo it the same way, provided that is working. I can still do the same way. So it's going to save me some time to re-explain same thing over and over again. Then I can try a record for other chapters. So you'll find that in one lesson we can cover maybe up to 3 questions. Then we are done. Next weekend we try another different question. So can you see, like now on our next lesson we'll still be doing the same chapter but a different question. Can you see? So that's what I'm saying. Maybe on our next lesson, let's try if it works and see how far we can go with it. Then from there, otherwise, if it doesn't, we'll just try to find a way in which we can possibly do this. Otherwise, if it doesn't work, you might find that we'll just try if I do a summary, a summarized video, then watching, explaining, then from there manually solve the questions. We'll just try to find a way to make it work, just so that we can cover a lot but in just one video. And again, in case if you need a revision of the same chapter, I won't have to redo it again like this, unless if the other option is just for you to watch this lesson again. But can you see, it's 2 hours but just one question. I'm not sure if you understand what I'm trying to say there, Albie.
Yeah, sure. So
Yeah, so I think we'll just try to make it work. Oh, and the other thing, LB, I wanted to say is just that I'm not sure if you are aware or you are not aware. You remember that time when you were writing, when was it? I think you were writing on Tuesday and Friday or something. So I wanted to say, with us doing those lessons during the week, it was going to be a favor and not an everyday thing, because the one-on-one are only on weekends. I noticed it's because we couldn't do those lessons on that weekend. That's why I was willing to do it over the weekdays. So it's unfortunate during weekdays my schedule is very, very tight, in a sense that after work I prepare for lesson, then after lesson I prepare to sleep. So you can see in between there's no enough time. So I'm not sure if you were aware that the one-on-one are only on weekends. LB. LB.
wait,
Are you
sir.
still there?
Can you just wait? I wanna check something, ne?
Oh, okay.
Wait. I wanna read something here. There on your pinned message, right? You said
Oh, you're
that the
checking
master
that one. Let
classes
me
plus
check.
revision plus study ahead. Then you said special revision days before writing a test or an exam.
Let me quickly do this. Let me do this. For now, I can. Okay, let me stop